All right, chemistry, so we're following up our lesson on acid interactions with a similar lesson on base interactions. So, strong base in water, we've talked about this already, it's just going to completely dissociate into hydroxide ions, and hydroxide ions are what define a basic solution. Weak base in water accepts some, usually a very small number of protons from a water molecule. They basically break a water molecule in two, and that leaves behind the OH minus from the water molecule, and that's hydroxide. That's a basic solution as well. Excess strong base with strong acid, so you have both of them in solution, but you have more of the strong base. So that's going to be a complete dissociation of the protons from the acid to the base to neutralize it. That'll be a neutralization reaction creating water, H2O. Then the remaining strong base, the OH minus, remains. And finally, excess strong base with a weak acid, it's going to be the same thing. It accepts all of the protons from the weak acid to produce H2O, and then the remaining OH minus from the strong base remains. And again, weak acid, weak base, we don't discuss that. Okay, so strong base in water, complete dissociation of the hydroxide. So there you have water. You have a representation of one of the water molecules over on the left. So in the acid-base section, we dealt with bases reacting with water. So sodium hydroxide is a strong base because it contains its own OH minus ion. It brings it along its own hydroxide. So in water, a strong base will completely dissociate into the metal cation, that's the Na, and the hydroxide, the OH minus. The creation of a hydroxide ion, OH, is what defines a base and can react with an acid. The metal cation, sodium, does not react any further. It just becomes a spectator. Next, we have weak base in water that accepts some, usually a very small number of protons from the H2O. It breaks the water molecule in two, producing OH minus. So here we have two weak base molecules. They're ammonia. We're going to drop them in the water. So when a weak base such as ammonia, NH3, is placed in water, it will occasionally pull a proton, H+, away from a water molecule. So there we see that proton is going to move over to one of the ammonia molecules, like that. The result is the ammonium ion NH4+ and a hydroxide ion OH-. In this situation, water acts as an acid by donating a proton to the ammonia. The ammonium ion NH4 is the conjugate acid of ammonia. Hydroxide OH- is produced when the water molecule loses a proton. Next, we have excess strong base with strong acid. So that's a complete dissociation of the protons from the acid to the OH base, and that neutralizes the base, so that creates water, H2O. Then the remaining strong base, because you have excess strong base, OH- remains. So here we have, on the left, we have one strong acid molecule, hydrochloric acid, on the left, and on the right we have two strong base molecules, sodium hydroxide, NaOH. In this example, there are more molecules of strong base, NaOH, than strong acid, HCl. So we're going to put both of those in solution, and the first thing that's going to happen is, we'll go ahead and put the acid in solution too. So first, the NaOH will be placed in the water, and the Na plus and OH ions will dissociate. So that's going to go like that. OH minus ions will accept H plus protons from HCl 100% of the time. So there goes the proton, and that neutralizes the OH to become a water molecule. This creates a neutral H2O molecule, leaving just one OH minus in the solution. The solution was basic before the HCl entered the solution. After the HCl reaction, the solution is still basic, but less so. It only has one OH minus instead of two. Finally, we have excess strong base with weak acid, and that's going to be the same as with a strong acid. Okay, so in this example, there are more molecules of strong base, NaOH, than weak acid, HF. First, the NaOH will be placed in the water. There it goes. The Na and OH ions will dissociate, as you just saw. We care only about the hydroxide OH minus ions. The Na are spectators. Next, the hydrofluoric acid is placed in solution. The order doesn't matter, but we're just doing it in a sequence so it makes the process clearer. The OH ions will accept protons H+ from the weak acid, such as HF, 100% of the time. So any weak acid, any molecules you have will automatically neutralize any hydroxide ions like that and turn them into water molecules. This creates a neutral H2O molecule, leaving just one OH- in the solution. The solution was basic before the HF entered the solution. After the HF reaction, the solution is still basic, but less so. There's only one OH- instead of two. Now, what's going to happen if we put a lot of weak acid in with a lot of strong base? Here we will place several weak acid HF molecules in solution with a strong base, sodium hydroxide. Place the NaOH in the water first, but again, it really doesn't matter. We're just going to do it in this sequence. The NaOH will dissociate into Na plus and OH minus, as you see. It is only the OH minus that is important. The HF weak acid is next placed in the solution. So then the question is, how many of the HF will dissociate to hydroxide ions? We know if it's just water, only a few of the HF will dissociate to water molecules. But if there's hydroxides, how many? The hydroxide OH- has such a strong pull on protons that it will cause 100% of the weak acid molecules to dissociate. This means that every weak acid molecule that enters the water will give a proton to a hydroxide ion. In the presence of hydroxide ions OH-, a weak acid will 100% dissociate to a hydroxide, but not 100% to water. This means that a weak acid will neutralize, turn to water molecules 100% of the strong base OH- ions that are in solution. And weak base and weak acid we do not deal with. So that takes care of our lesson on base interactions, and now you're ready to start talking about a more advanced topic called buffers.